Hello, so I will be introducing myself first. So, this is the week 12 live session. So, I am Anjali Negi. I am a PhD student currently pursuing my PhD in IIT Kanpur. And yes, so let's start. I will share my screen. So, before that, I will wait for 2-3 minutes and then we will start.
Hello everyone. In this video, I will be solving GATE 2017 Chemistry question number 38. This question state that if delta naught is the octahedral splitting energy and P is the electron pairing energy, then the crystal field stabilization energy CFSE of this complex coordinate complex is. So we have to find out. Hello everyone. In this video, I will be solving GATE 2017 Chemistry question number 38. This question state that if delta naught is the octahedral splitting energy and P is the electron pairing energy, then the crystal field stabilization energy CFSE of this complex is. So we have to find out the CFSE of the given complex. To the crystal field splitting in an octahedral complex. So in an octahedral complex, this state represents the degeneracy of all the 5d orbital in the isolated central line, and the state 2 represent the hypothetical degeneracy of all the orbital at a higher energy level. If the negative charge of all the ligands is assumed to be uniformly affecting the electrons in the d orbital of the metal line. So the state number 3 is actually this represent the crystal field splitting. So in octahedral complex, as our so in an octahedral complex, the coordination number is 6, and the metal ion is at the center, and the ligand occupy the sixth corner of the octahedron. Okay, so x square minus y square and dz square are oriented along the axis, and the other orbital remain in between the axes, which are dxy, dyz, and dzx. So in case of octahedral complex, these two orbitals are designated as EG. So in octahedral complex, these two orbitals are designated as EG, and the other three are T2G. Okay. And as the ligand approaches the central line, along the axis, the electron is present in the EG orbital, so is repelled more by the ligand electrons than the in comparison with the T2G one. Hence, we see that the energy of the dz square and dx square minus y square, these orbital, is much more in comparison to the dxy, dyz, and dzx orbitals. Okay. And the splitting energy, that is delta naught, is the crystal field splitting energy, and this is actually, if we say this is from the barycenter, it is plus x, and from the barycenter T2G is stabilized as y. So we will say x plus y, if it is equal to delta naught, which is my CFSC, is equal to 10 dq naught. So my x is in octahedral field is equal to 3 by 5 of delta naught. That is the, in terms of dq, it is 6. And y is 2 by 5 of delta naught. In terms of dq, it is equal to 4. So T2G electrons, each of them is actually stabilized by minus 4 dq. And electron in the EG and EG electron are destabilized by plus 6 dq naught. These are actually with respect to the unsplit barycenter, which is here. And hence we can say that the total energy of the system is conserved before and after splitting. Okay. So the ligands which causes a large splitting delta of the d orbital are referred to as the strong field ligands, and the complex such as uh, uh, This, for example, given below is called a low spin. And the example of one ligand is NO2 negative. So in this complex that the example is shown below is actually we can see that the delta not is so large that pairing is possible in this case. Okay, so we see that no electron is in an EG orbital, but there is a pairing. Wait, so if we have taken D5, for example, so initially it was all unpaired electron. Okay, and after the strong field ligand it experience octahedral splitting, uh, where the delta naught value is very large, the CFSE is very large. So pairing take place, and this complex looks something like this. Now the ligands, for example, iodine I negative and Br negative, which causes a small splitting delta of the d orbital, are referred to as a weak field ligand, and and the complexes are known as high spin complex, which are formed. So this is the example of a high spin complex for a D5 electron system, electronic configuration. So we get delta naught as delta naught is very small, so no pairing take place in this. So in high spin complex, always remember that pairing doesn't take place. Okay, so in general this is a crystal field splitting energy increase as the ligand varies in the following order. So in the following order, if we go from left to right, we see that there are there is an increased value of the delta. So there is a higher splitting, and so I can say that CN negative is a strong field ligand causing a higher delta naught value. Okay. Now let's solve our question. So our question is that yes. So my question was to solve the to find out the CFSE of the given complex. So for the given complex, my cobalt is in 2 plus oxidation state, where I can write the electronic configuration as this, which is 3d7. So 3d7, before I fill up the electrons in the T2G and EG orbital of the of my complex, I should first note 2 points. The first one is that ammonia is actually considered as a is considered as a strong field but in case of cobalt 2 plus, we see it that the that it makes a high spin high, high spin complex, and in case of cobalt 3 plus, it makes a low spin complex. So yeah, also here you can note that as the charge or the oxidation state of my metal ion increases, it also affects the CFSE, such that as the oxidation state increases, my delta naught values also increases. Okay. No. So when we fill this, my complex is in high spin because my oxidation state of my cobalt is 2 plus. So this will be 1, 2, 3, okay, 4, 5, 6, 7. And this was 1, 2, 3. So we note that in high spin, complex, no pairing energy is there, okay? Because no pairing is taking place besides the one which are already paired. So the CFSE of cobalt 2 complex which is given will be, so there are total 5 into minus 4. So the CFSE of cobalt plus 2 will be 5 electron in T2J, which will be minus 0.4 delta naught, plus there are 2 electron, so 2 into 0.6 delta naught, giving me the value of, so giving me the value of minus 0.8 delta naught. So the correct option for the question number 38 is that option number C. Okay. For this, I will refer you to go through the lecture Bonding in Complexes 3 by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. This is a YouTube link for that. Thank you.
So I hope we can move forward, and I will, if you have any doubt, you can type in the chat box.
Hello everyone. In this video, I will be solving GATE 2013 Chemistry question number 43. This question states that the correct electronic configuration and spin-only magnetic moment of gadolinium 3 plus ion are. So first we have to define the electronic configuration of gadolinium 3 plus ion, and then we have to calculate the spin-only magnetic moment. So let's solve the problem. here, here we have the inner transition elements known as F block are actually divided into two categories, that is lanthanoids and actinides. So these lanthanoids are the 14 element series which are followed by lanthanum, and actinides are the 14 elements following the actinium element. Okay, so that is why the name defined as lanthanoids and actinoids. So basically, the electronic configuration for lanthanoids, the electronic configuration of all the tri-positive ion, the most stable oxidation state of all the lanthanoid. So tri-positive ion is actually the most stable electronic configuration for all the lanthanoids, and that will be in the form of 4FM. So that is because if we look into the general electronic configuration of any lanthanide metal, uh, any lanthanide element or metal, so we have xenon, okay, and then 4. So xenon has atomic number 54, and then after 4f, 1 to 14 number of electron, and then 5d, 0 to 1 electron, or 6s, 2. So when we have a tri-positive lanthanide ion, so these 2 from 6s and 1 electron from 5d will be as a valence electron and will be removed, and only the 4f electronic configuration have the electrons in it. Okay, so yes. So the gadolinium that we have, it has an atomic number of 64 value. The electronic configuration, we can simply write it as xenon 4f7, 5t1, 6s2. So for gadolinium. But in the case of gadolinium ion, GD3 plus that we have, so the electronic configuration becomes as xenon 4s7, correct? So this is half part, and then to calculate the spin only magnetic moment, so when the electron, spin only magnetic moment comes, so basically when electron moves freely, it will generate a magnetic field, correct? And this magnetic field is generated by the motion of the electron, and further, which is known as the magnetic moment. But when a electron rotates on its own axis by generating a magnetic field, it is known as the spin only magnetic moment, and we can calculate it as under the root n bracket n plus 2 whole, and it is denoted in Bohr magneton unit, where my n is actually the number of unpaired electrons. So for gadolinium 3 plus, remember we have this electronic configuration, and hence we have 7 unpaired electron in total. Okay, so if I have 7 unpaired electron in total, so I can actually calculate, uh, so my n is equal to 7 and my mu will be equal to 7 plus 2. Okay, so once I solve this, I will get 7.9 Bohr magneton, and hence my option number A is actually the correct option. And I will recommend you to go through lecture D and F block elements by Professor Debashis Ray, Department of Chemistry, IIT Kharagpur. Here is the link below. Thank you.
So moving forward to the next problem.
GATE 2013 Chemistry, question number 42. This question states, the increasing order of melting point of halides NaCl, CuCl and NaF is. We are given with 4 different options. So we will look into the order of the melting point, but before that, let's move into some basic. So halide of the elements are we can make the bullet points as number 1, the S block halide are predominantly ionic because my S block elements have more metallic character in the periodic table. The P block halides are predominantly covalent because of the non-metallic nature of my elements in P block. In the D block, low oxidation state halide tend to be ionic and high oxidation state halides tend to be covalent in nature. So keeping these points in mind, we know that the melting point is directly proportional to the ionic character. So as the ionic character of my metal halide increases, the melting point of that metal halide also increases. Okay, so now we are given with CuCl, NaCl and NaF. Since if we compare the size of the halide, we know that my fluoride ion has very smaller size in comparison to chloride ion. Correct? Also, the electronegativity of both of them is in the order of this, where my fluoride ion have a higher electronegativity in comparison to the chloride ion. This is due to the small size, or we can say high charge in a small volume. That is the charge density. That is makes the my fluoride ion as highly electronegative anion. Okay. So now, when we compare the ionic character in between the given chlorides, CuCl, NaCl, and NaF, we get to the order where where we can simply write that my NaF has the highest ionic character, and then NaCl, and then finally CuCl. Okay, where my copper belongs to the D block element. So here, it is the same trend that follows in the ionic character as well as in the melting point. So the given options that we are for the order of the melting point in increasing order for the given halides will be, so option A is the correct option here, as NaF has the highest ionic character as well as the melting point, then NaCl, uh, uh, and then CuCl. So we have seen why my fluoride ion is actually highly electronegative, making my NaF is more ionic in nature than the NaCl. And in comparison to CuCl and NaCl, we can say that my Na belongs to S block and have a very high metallic character, and that is why NaCl is more ionic in nature and having higher melting point than CuCl. So I will highly recommend you to go through the NPTEL reference of by Professor M.S. Balakrishna, main group chemistry, Department of Chemistry, IIT Bombay. The link is attached below. Thank you.
Okay, moving forward.
everyone. In this video, I will be solving GATE 2018 Chemistry question number 46. This question states that at the temperature T, the canonical partition function of a harmonic oscillator is with fundamental frequency mu is given by. So this is the expression for the canonical partition function of a harmonic oscillator. So we have to find the probability of the harmonic oscillator in the ground state given h mu by kBt is equal to 3. So before solving this question, let's have some basic here. So when we talk about the canonical partition function, it is the ensemble of microstate So when we talk about the canonical ensemble, so when we okay, and a constant volume V, and they are at a thermal equilibrium, that is T, correct? And they can be actually considered as an ensemble of microcanonical sub-ensemble. So like this small box can be considered as a sub-ensemble of microcanonical. Okay. So these among these microcanonical ensemble, we have a difference in energy. Okay. But as a super ensemble, which I am calling it as canonical ensemble. Okay. So under this particular sub-ensemble of microcanonical ensemble is actually having a constant energy E7. Okay, but among each other they can exchange the energy. So this is what we call a super ensemble, and so this is isolated. Okay, and having temperature T. Now, so this is actually the representation of canonical ensemble. So here the energy of each system can fluctuate. The system are however kept in a fixed temperature T by putting the super system in a bath, and we establish a thermal contact between the individual system. So each system is actually at a constant NVT. Okay. Now, so here, if we look into the energy distribution, so this is the distribution of particle in a canonical ensemble having a set of energy value from say E6 to, from say E6 to E10. Okay, so we are going from E6 to 10 as here shown in the figure. So the arrow indicate the particles and the horizontal line are energy levels here. So you can see that in the distribution in energy is equal to 10 is actually we get only two different distribution, and for energy equal to 8 we get four different distribution, and similarly we get for energy 6 equal to 6 is we get 1 2 3 5 different distribution. Okay. So it is vital to note that all the microscopic state with the same energy are equally likely. So The microscopic state 1, 2 are equally likely with the same energy, and the four and all the four arguments with e equal to 8, that is here, are equally likely, or in e equal to 10, the two different arrangements are equal to are equally likely. So, however, the state with the different energies have different probability, and they contribute differently to the overall observed macroscopic property of the system. So, here it is important to find out the probability of a state with a given energy. So now you know why it is very important to find out the probability of each state with a different energy, because they all contribute differently to the overall observed macro state property of the system. So what is the probability of the jth state Pj that being occupied is actually written as Pj equal to small nj asterisk upon capital N, where small nj asterisk is the desired most probable distribution of the jth state, and capital N is the total number of NV system in the ensemble. So we can actually write it as e to the power beta, uh, uh, where my beta is equal to 1 upon kBt. Okay, and Ej is the energy, and here in denominator you get the sum over all the states, that j states, and we get the exponential to the power beta Ej, energy Ej. Okay, so the term in the denominator is actually termed as the canonical partition function, Q, with constant NVT parameter, and the thermodynamic quantities like free energy, entropy, etc. can all be obtained from Q. So these relations form an important part of statistical thermodynamics. Now, okay, to solve our problem, we know that my probability, we have to find out for the ground state. So my probability for ground state, that is j is equal to 0, will be p0 is equal to n0 upon capital N, which will be written as the exponential e minus e0 upon kbt, and upon the canonical partition function for the given. We are given with the ground state, harmonic oscillator. So this expression will be E minus E0 upon kBt upon e to the power minus h mu upon 2 kBt 1 minus e to the power minus h mu upon 2 kBt. Correct? Also, this energy expression E0, so we have to write the energy expression E0. For our harmonic oscillator, the energy expression is given as mu plus 1 by 2 h cut mu, where this is my vibrational quantum number. So this goes from 0, 1, 2, etc. So for E0, it will be 1 by 2 h cut mu, or we can write it as h mu, right? So this expression becomes P0 is equal to e to the power minus h mu upon, here it will be 2 by 2 kBt upon e to the power minus h mu upon 2 kBt, and this expression comes up, and we can get e1 minus e to the power, and I can actually write it as minus h mu upon 2 kBt. So this cancels out, and my expression again becomes, so 1 minus e to the power minus h mu upon 2 kBt. Okay, and we are given that this particular part is equal to 3. So my expression becomes 1 minus e to the power, a minus sign, and 3. So when I solve this, my probability is equal to 0.95. So we have to write the probability of finding the harmonic oscillator in the ground state is 0.95. Again, I will recommend you to go through the book Statistical Mechanics for Chemistry and Material Science by Professor Biman Bakshi, and the particular lecture Canonical Ensemble Part 1 by Professor Biman Bakshi, and Part 2 also. So, Department of Chemistry, IIT Bombay and IISc Bangalore. So this is the link attached here. Thank you.
So the last problem, so I will share.
Hello everyone. In this video, I will be solving GATE 2012 Chemistry, question number 32. This question states that consider the phase diagram given below. So we are given with the phase diagram of component A, component B. And at the intersection point capital Q, the phases that are in equilibrium are. So we are given with 4 different options, and we have to find the correct option that define the phase at a point Q. So let's move into some basic. So the phase diagram or equilibrium diagram is a diagram in the space of relevant thermodynamic variables, example temperature and composition, or pressure and composition, indicating phases in equilibrium. This is called as phase diagram. Now the phase diagram of two component system can be in liquid-liquid phase, in liquid-vapor phase, in liquid-solid phase, or in gas-solid phase. Now, in a given problem, we are discussing the liquid and solid phase of the two component system. So, yes, so the axis for the two component system, the temperature axis. So if this is the temperature axis and this is my component in my problem, I will discuss this in a similar manner. So this is say component P, and the another is S. Okay. So this is again the temperature axis. Now there will be some one point in the temperature axis where it will be a melting point for my component P, above which it will be a liquid and below which it will be a solid. So if I join these two temperature axes of the component P and S in this manner horizontally, then this will be known as the composition axis. Now the composition axis is such that it start from 0 and it goes to 100. That is, 0 means it is pure P and 100 means it is pure S. Now in between it will be a 50-50. So it will be 50% of component P and 50% of component S. Now we can denote the composition axis as weight percentage, okay, from 0 to 100. For a given problem, so we are actually given with the, I will just draw it here. So this is a separation line for solid, X plus Y. So actually, yeah, so I have been given component X and component Y, and P and S are the 2 points. So yes. And Now, here it is given that it is pure liquid. So if I am talking about a point, say, so this is P, this is Q, this is R, and this is S, okay? Yes. Now, this is 288 Kelvin, it is given. So actually we are given with a mole fraction of Y, okay? So we can either denote it with the weight percentage or mole fraction. So just we will discuss the fundamental here. So at point Q, if you look at point Q, what you will find? You will find that it is placed with a composition of liquid of X and Y both. So it is the system where my system is in all liquid phase, okay? So I will just write it X and Y in liquid phase. And as it was given in the question that the starting point is say P and then Y is added until the composition reaches S. So if my starting point is P, also my P belongs in between of a solid and a liquid region. So this particular region is actually not pure solid or pure liquid. So it will be at P. So my X is the starting here. So it will be more of X, correct? And my Y is adding up. So we can say that it is in a solid plus liquid region. Okay. Now, because it is not specifically on the axis, so I cannot say it's a pure X or not a pure X. So I will not talk about the composition of X and Y here, but it is the solid and liquid are present in almost equal proportion, we can say, because it is almost at equal distance from both the separation lines. Okay. Also, yeah, let's go move into another point at R. So R is a point that is lying exactly on the line, which is the separation or the equilibrium line between liquid, okay, and solid. So this is at equilibrium between, not exactly solid, but yeah, equilibrium between liquid and liquid plus solid phase. Okay. Now the last point that is at R, at S. So this is the again similar like P. So it will be the system which is having solid plus liquid phases together. Solid plus liquid phase. So I can in the given problem we are actually given with the option that at S the system has more solid than liquid. But yeah, maybe it is true. So we cannot specifically say, but yeah, more solid than liquid, but it is in a liquid and solid phase. So finally, in my phase diagram, I can actually define my phase diagram as, so here we have component AB2, and this portion is actually is a composition of solid A plus solid AB2. And here it's a solid AB2 plus solid B. Above this, it's a solid A plus liquid A, and here we have AB2 as solid plus liquid AB2, correct? And just above here we have as my solid B plus liquid B. Now the Q point is an intersection of two curves. So first curve here is an equilibrium between the AB2 solid and the liquid AB2 with is in equilibrium with the whole liquid. Okay, and similarly my another curve is equilibrium between B solid B and liquid B. So we have at point Q. So if you look at, so we have solid AB2 and the liquid AB2 in our two different options. However, the solid is at Q is can only be B, because A is not present here. So you can just look at this point, and so this we have the intersection of these two curves, where at these two curves we have either solid B or either solid AB2. Okay, and so hence the option that should be correct for to define the phase Q, it should be solid B present with solid AB2 and liquid AB2. Okay, so the correct option is C. So here, I will recommend you to go through the NPTEL reference phase diagram introduction by Professor Rajesh Prasad, Department of Applied Mechanics, IIT Delhi. So here is the link below. Thank you.
So if you have any further doubts, you can either ask now, or I have also shared my email ID with you, so you can also connect with me there. So thank you so much for joining. Thank you all. So I will end the session. Yeah, thank you.